Hello everyone, welcome back to another episode of Study Sheet and Addendum's Midterms in a Pod. This time we are reviewing the first half of the semester of Waves with Professor Vinet. So, let's get into the questions right away, Professor. So, what is simple harmonic motion? And how does it relate to the waves that we study for most of the semester so far?
So, simple harmonic motion, what you have to understand is that the word harmonic really means periodic. It means a motion that repeats. And simple harmonic motion is a particular type of repeating periodic motion where you can describe the motion using a sinusoidal function. Or a cosine. A sine function and a cosine function are essentially the same thing, as you probably know. So this happens in order to get periodic motion. What you need to have is a restoring force. So you have a force that always tries to bring the system back to some equilibrium state. So as soon as you displace the system from equilibrium, there's going to be a force bringing it back that tries to bring it back towards equilibrium. And that's what happens with the mass on a spring. If you stretch the mass, it's going to pull, if you stretch the spring, it's going to pull the mass back towards the original length of the spring. And if you compress the spring, it's going to push the mass back towards the equilibrium position. And to get simple harmonic motion, that force that you get, that restoring force, has to be proportional to the displacement away from equilibrium. So if you're twice as far away from equilibrium, the force is twice as big. And what you see when you analyze the mathematics of that, you see that this leads to motion that can be described by a sine function or a cosine function. And it's interesting in terms, it relates to waves because what we see when we look at a wave, we see a medium that is actually oscillating. If we look at each piece of the medium, it's actually oscillating in simple harmonic motion. If we're looking at a sinusoidal wave, each piece of the medium is oscillating in simple harmonic motion. So that's why we start the semester by looking at simple harmonic motion. And then we study waves where each piece of a medium is undergoing simple harmonic motion, but pieces of a medium that are next to each other are at slightly different places in their oscillation. So that's what creates the wave that travels through the medium.
I see. So another concept that we've also been struggling with is that what's the difference between the wave speed and the velocity of a particle then?
Right. Well, you have to think about the fact that each piece of a medium is moving in simple harmonic motion. Right, so the pieces of the medium, their velocity is changing as time goes by, right? Because in simple harmonic motion, when the medium is at maximum displacement, for example, it momentarily stops and then it turns around. And when it's at equilibrium, it's moving very, very fast. Well, it's moving the fastest that it moves, right? Because as soon as it crosses equilibrium, it starts to slow down because it's either being pulled back to equilibrium or being pushed back to equilibrium. So it's going to slow down. So there's the motion of the medium, which is simple harmonic motion, and there the velocity is changing as time goes by. It's described by a sine function. But the wave itself is the speed at which the disturbance, the crests and the troughs that the wave is made of, are actually moving through the medium. So the wave speed tells you how fast the crests of the wave are moving, and the transverse speed or the transverse velocity is telling you how fast a particular piece of the medium happens to be moving. But you have to understand, when there's a wave, right, it looks like the crests are propagating through the medium, but the medium itself is not moving from place to place. So an example I give my students when we introduce waves, I have them do the wave like at a sports event, right? The crowd doing the wave around the arena, for example, if the Habs happen to reach a Stanley Cup Finals, for example. And what happens there, nobody is actually moving from one seat to the other around the arena. Everybody is just getting up and sitting back down, but that creates a movement of a wave around the arena. So nobody's moving. The medium in that case is the crowd, and nobody is actually changing seats, but there is a wave that's propagating around the entire arena. And that's what's going on with waves. So every piece of the medium is just oscillating around an equilibrium point. But the wave itself is propagating through the medium. And when we talk about wave speed, we talk about the propagation of the wave through the medium.
I see. I think one of the reasons why we struggle a lot with this concept is because a wave is also, we've been told that a wave doesn't displace particles and it only moves energy through the medium. But at the same time, it's like the particle itself is getting displaced a little bit.
Well, the particles are getting displaced. But if you look at what the particles are doing, they're just doing simple harmonic motion. So there's no net displacement, I think, of the medium is a better way of saying it, right? So every piece of the medium is undergoing motion, but it's around the equilibrium point. So on average, there's no motion of the medium at all, right? So every piece of the medium is moving around some equilibrium point. So it's going on one side to a distance A and on the other side to a distance A. So if you look at the average position of every piece of the medium, it's always at equilibrium on average. So there's no net displacement of the medium. So that is correct. But it doesn't mean that the medium is not doing anything. Because if the pieces of the medium were not doing anything, you wouldn't have a wave.
Thank you for clarifying.
Okay.
So another question we have is which variables are related to the characteristics of the medium, of the source, and of the particles? And then how do these variables affect our calculations?
I'm not sure what you mean by that. Which variables? Can you list some variables that you're thinking about?
So this was a listener question, so I will probably take my own interpretation on it.
Okay.
I think what they mean is what are some factors influencing the characteristics of the medium, of the source? Not sure what they mean with the particles.
Yeah, I'm not sure either. I mean, there's a few things there, I guess. The medium itself is the thing that determines the wave speed, right? So what we've learned in class is the specific example of a wave on a string, where the speed at which a wave will propagate along a string depends on the tension in the string and on the density of the string. And you all just had a lab last week, I think, where you actually saw that in action. By hanging different masses off the string, we could control the tension in the string. And we actually used two different strings. One of them was red, the other one was black. They had different densities. And in that case, what that changed was the speed at which waves were traveling back and forth along that string in the lab. So those are things that are related to the medium, right? So those variables, the tension and the density, those are related to the medium, and they are the things that tell you how fast a wave is going to propagate in that medium. And then I'm not sure what exactly the question is getting to in terms of other variables there, but we also know that the wave speed is equal to the wavelength divided by the period. And that one, the way to remember it is a wave moves forward by one wavelength in a time of one period. And we know that speed is distance over time. So wavelength divided by period. I think on the formula sheet, it actually says it has the V equals lambda F version of that relationship, but it's really one wavelength in one period. That's also the wave speed. But the wave speed is really set by the medium itself. And then if you shake a medium, if you disturb a medium at a certain frequency, then the wavelength will adjust depending on the wave speed. You have no control over the wave speed, right? It's the medium that sets the wave speed. So I hope this helps a bit, but I'm not sure exactly if that's what the listener was getting to there.
Yeah, I hope this provides some clarity for them as well. So the next question is the famous, what is the phase constant and how do you find it?
Yes. Yeah. Okay. For this one, it really helps. I really insist with my students that they look at the unit circle, right? And we're describing the motion of a mass on a spring. Let's just look for the time being at a mass on a spring. You're describing the motion of a mass on a spring using a cos function. And inside the cos function, you have an angle. And the mass is moving as time goes by because the angle in the cos function is changing. That's what leads to the motion of the mass back and forth. So the cos function oscillates between +1 and -1, right, as the angle changes. And the mass oscillates between +a and -a as the cos function goes from +1 to -1. And at every point of the motion of the mass, right? So you can imagine a mass that starts, let's say you take a spring, tie it to a mass, and you stretch the mass and bring it to +a, and then you just release it. So it's going to be pulled back. It's going to speed up until it reaches x = 0, the equilibrium point. By that time, it's moving very fast, so it keeps going, and it starts to compress the spring, and then it's going to start slowing down. It slows down until it reaches -a. And then it's going to turn around and start speeding up towards x = 0 again. And then eventually cross equilibrium again, moving back towards towards +a. And then it's going to be pulled back by the spring. It's going to slow down until it reaches +a. And then the whole motion will just repeat over and over again. At every point, I mean, the cos function started out, it was equal to 1 when the mass was at +a. And then the cos function has to decrease as the mass goes to x = 0, and then it becomes -1 as the mass goes to -a, and so on and so forth. So the reason the cos function is changing is because the angle in the cos function is changing. So that angle in the cos function has a specific value for every point along the motion of the mass. So it has a value when the mass is at +a. It has a value when the mass is at x = 0 and moving towards the left. It has a value when the mass is at -a. It has a value when the mass is at 0 and moving towards the right. And it has a different value when it reaches x = a again. So that's what we call the phase. That's the angle inside the cos function. Okay? And if we start, let's say we start at +a, since cos of 0 is equal to 1, you could say that the angle initially was 0, and then it increases. And when the angle reaches pi/2, cos of pi/2 is 0, so that's when your mass reaches x = 0. And then the angle keeps increasing. Eventually, the angle is equal to pi, and cos of pi is -1, and that's when your mass is at x = -a. And then the angle keeps increasing again, and eventually it's equal to 3pi/2, and that cos of 3pi/2 is 0, and the mass is at x = 0 again, but now moving towards the right. And eventually the angle becomes 2pi, and the mass is back at x = +a. So we've done a full cycle this way, and the angle has gone from 0 to pi/2 to pi to 3pi/2 to 2pi. So at each of those points, the angle has a specific value, and the value of the angle corresponds to a specific point in the motion of the mass. And the phase constant is simply the value of the angle when you start looking at your mass. In the example I gave you, you started when the mass was at x = +a. So the angle in the cos function initially was equal to 0, right? So that at your initial time, at t = 0, you would have said that the angle is equal to 0. So in that case, the phase constant would be 0. But you could also decide that instead of starting to look at the mass when it's at +a, you could decide, I'm going to start looking at the mass when it's at x = 0 and moving towards the left. Right? You're free to start looking at that time. It's like in the first lab when you press start on your record button for the mass oscillating back and forth on the track. Right? You didn't have to press start. You could press start whenever you want. So the phase constant is just the value of the angle when t is equal to 0. So if you start looking at your mass when it's at x = 0 and moving towards the left, then the angle that corresponds to that is pi/2, because cos of pi/2 is 0. And if you're moving towards the left, it means the cos function is decreasing. And if you look at your unit circle and the angle is getting bigger and bigger, when the angle is pi/2, you're at the top of the unit circle, right? But you're turning counterclockwise. So So the cos function goes from being 0 to being negative. So at pi over 2, that's when the mass is at x equals 0 moving towards the left. So your phase constant, if you start looking at your mass at that time, if you decide to say, this is my initial time, when the mass is at x equals 0 moving towards the left, then your phase constant has to be pi over 2. Because when t equals 0, the position of the mass is described by x of 0 is equal to a cos of pi over 2. So you have to have a phase constant of pi over 2. So that's the only thing the phase constant represents is the value of the angle inside your cos function when you decide to start looking at the mass and describing its motion. And I know it gets confusing because mathematically, I mean, you have to do inverse trig functions to solve for it, but conceptually, it really just represents what is the value of the angle when I started looking at my mass.
Okay, so that was for simple harmonic motion.
Yes.
When it comes to waves, though, like an actual traveling wave, how do you find out what's the phase constant value? Because I know it changes depending on whether, like on the snapshot graph, the wave is moving to the left or it's moving to the right. How do you determine the phase constant value?
Yeah. So it's a bit tricky. You have to watch for a few things there. So first of all, when we were doing simple harmonic motion in the first part of the semester, we're studying simple harmonic motion, and we pretty much always describe, at least the textbook always describe the motion using a cos function. And your equation is always x of t is equal to a cos of omega t plus phi naught. So if you imagine what the angle in the cos function is doing as time goes by, the angle just gets bigger and bigger, right? Because if t gets bigger, omega t plus phi naught gets bigger. So on the unit circle, you have to pay attention to what's happening along the horizontal line because you're looking at the cos function. The cos function describes a displacement in this case. This describes x. And the angle is always getting bigger, so you're always turning counterclockwise along the unit circle. And if you pay attention to that, you can figure out in each of the 4 quadrants, is the displacement positive or negative? And is the velocity positive or negative? And you can sort of make a little diagram where in each quadrant you just make a note of displacement positive or negative, velocity positive or negative. When we're doing wave motion, the equation we're using, in most cases, we use a sine function instead of a cos function. And that's just convention. That's just what the textbook does. It would be fine to use a cos function to describe a wave, but it's just not what we're doing. It's a choice the books have made. Pretty much all textbooks do it that way. So then when you're looking at your unit circle and you look at the angle and you want to figure out is the displacement positive or negative and is the velocity positive or negative, you have to be looking at the vertical axis because it's the sine function is describing the displacement of the medium, right? So that's one difference between what we did in the first chapter and what we did in the second chapter of the course. You have to look at the vertical axis. The other thing you have to watch out for is we are using the equation for a traveling wave is sine of kx plus or minus omega t, right? And if the wave is moving towards positive x, then we are going to use sine of kx minus omega t. And if the wave is moving towards negative x, we're going to use sine of kx plus omega t. And this is important because if your wave is moving towards the right, then it's described by sine of kx minus omega t. What that means is the angle inside your sine function, as time increases, as time goes by, this angle is getting smaller, not bigger, right? Because the angle is described by kx minus omega t, plus phi naught, of course, right? But since it's kx minus omega t, when time gets bigger, the angle gets smaller. And on the unit circle, that means that your angle is actually turning clockwise, not counterclockwise, because the angle is decreasing, not increasing as time goes by. So you have to look at what's happening on the vertical axis to your sine function, but you have to look at what's happening to it as you turn clockwise along the unit circle. And then you can figure out in which quadrants is velocity positive or negative for your medium. So that's something that I've noticed students have do struggle with, right? And then the other piece of the puzzle is, in most cases with simple harmonic motion, will tell you in the question, the mass starts at x equals, I don't know, 3 centimeters to the right of equilibrium, and it's moving at minus 5 centimeters per second or something like that. So you're given the position and the velocity. For waves, sometimes we can give you snapshot graphs. And from that snapshot graph, if we tell you the wave is moving to the right or to the left, you have to figure out the piece of the medium that you're looking at, is its velocity positive or negative, right? Is that piece of the medium moving up or down as your wave moves along the graph? And there you have to think, you have to imagine your wave moving, and then figure out if that piece of the medium moves up or down in a few seconds. So sometimes instead of telling you what the initial velocity is, you have to figure it out yourselves. So that's an added complication when we're looking at traveling waves.
So since we're already on the topic of like snapshot and
Yes.
history graphs, what exactly are these graphs? Like, what are their axes, and how do you go from one type of graph to another? Right.
So a snapshot graph, like the name implies, it's a bit like a picture of a wave at one instant. You have to be careful, and it's not exactly a picture of a wave, because your graph will be a sine or cos function, but it can also represent a longitudinal wave where the displacement is not perpendicular to the motion. So you have to be a bit careful there. But the idea of a snapshot graph is to give you a picture of the wave at one instant. So the axes will be displacement on the y-axis, and the horizontal axis will represent x. It will represent different pieces of the medium. So what you're seeing there is the displacement of different pieces of the medium at one particular instant in time. And that's why it's a snapshot. It's a picture of what the wave is doing at one instant. So from that, you can get the amplitude, right? Where you have the peaks, that you can read the amplitude off of that. And what you will read, if you look at the length of a full cycle on that graph, since the horizontal axis represents x, represents space, the length of a full cycle will be one wavelength. The history graph is showing you, it's going to look very similar, but what it's showing you is what one particular piece of the medium is doing as time goes by. And each piece of the medium is in simple harmonic motion. So it's going to be a graph of simple harmonic motion. On the vertical axis, you have displacement, just like on the snapshot graph, but your horizontal axis there is time. So what you're being told is one piece of the medium, what is it doing as time changes? So from that graph, you can get the amplitude the same as you can from the snapshot graph, because the maximum displacement is still the amplitude. But on the horizontal axis, if you look at one full cycle, since the horizontal axis represents time, one full cycle is one period, not one wavelength. So from the history graph, you can get the period and the amplitude. And from the snapshot graph, you can get the wavelength and the amplitude. And to go from one to the other, going from snapshot to history, I find that the best way of doing it is, if you're given a snapshot graph, make a few other snapshot graphs at various increments of time later on, right? And then you can make a little dot. Let's say that you're asked from that to draw the history graph for x equals 3, for example, right? And you have a little triangle moving along the medium towards the right or something like that. Draw it at different times and make a little dot at x equals 3 to see the displacement of the medium at x equals 3 at different times. And that's what you want to be graphing on your history graph. You're trying to graph the displacement of a particular point at different times. So it really helps to just draw a few snapshot graphs at successive times, if you're going to be asked to do that.
I see. Okay. So, I guess we'll skip a little bit ahead and move on to kind of, if the superposition of two traveling waves in the same direction gives another traveling waves,
Yes.
What does two traveling waves in the opposite directions give?
Well, that's a standing wave. So that's how you get a standing wave, is by having two waves traveling in opposite directions. And what happens there is there's going to be places where crests are always meeting crests and troughs are always meeting troughs. And that's a place where you'll have an antinode, where the medium will oscillate with very large amplitude. It'll oscillate basically with an amplitude 2A. But there's going to be places a bit further away where a crest from one of the waves is always meeting a trough from the other wave, and vice versa. So that at that point, the two waves are going to cancel, and that's where you find nodes. So places where the amplitude of oscillation is 0. So having two waves travel in opposite directions, instead of getting another traveling wave, you get a wave that's just standing still. In terms of, you don't have motion of crests and troughs through the medium. You simply have oscillation in place of the medium, with certain places where you have large amplitude and certain places where the amplitude is smaller, all the way down to 0. And that's why we call it a standing wave, because you don't have crests and troughs moving through the medium anymore.
So I heard that for standing waves, you also have to set boundary conditions, and that's how you derive the equations.
Yes.
How do you set those?
So the way that you actually can create standing waves, you need waves that travel in opposite directions, right? So in the real world, the way you're going to get that is by having waves bounce back and forth between boundaries of a medium. So in the lab, for example, where you had your string that was stretched between the motor and the pulley, when your motor was actually generating waves that traveled in one direction, but when those waves hit the pulley is a fixed point, and most of the wave actually just reflects back in the other direction. So you have the motor that was sending waves down the string in one direction, and those waves are bouncing at the pulley, bouncing back in the opposite direction. So you constantly have waves traveling in opposite directions along the string. And that's how you get a standing wave. But to do that, you have to have boundaries to your medium. And those boundaries can either be points where the medium has been physically fixed and prevented from moving. And that's what was happening in that example, right? At the pulley, the string was resting on the pulley. So the string couldn't oscillate up and down because it's just resting on the pulley and is being pulled down by the mass, right? So that piece of string cannot oscillate. So it has to be a node. And at the other end, at the motor, the motor was vibrating a bit, but very low amplitude, if you remember. So that piece of the medium was also being prevented from oscillating. So you had 2 points where the waves are bouncing back and forth, because at that point, the medium is being prevented from oscillating. So the only standing waves you can set up in that medium are standing waves where you're going to have nodes at those 2 locations. Okay, and then there's a few ways of doing that. Well, there's many ways, and you learned in class how to draw them. And it turns out that you can have a standing wave where you fit half a wavelength in that length of string that you had in the lab. That will be the first mode of oscillation. And then you'll have one where you can fit one standing wave in the length L. One wavelength in the length L, or you could fit 3 halves or 4 halves or 5 halves, et cetera, and that's how you derive that. The other kind of boundary to a medium is one where the medium is actually free to oscillate. And that seems a bit counterintuitive, that the wave would bounce back at a medium where it's free, at a boundary where the medium is free to oscillate. But it does happen, for example, with air in a tube. So if you have a tube that is open at both ends, so like a flute, for example, when the wave goes from the constrained medium that the tube is into an completely open room full of air, the wave does bounce back. Some of the wave actually reflects. Instead of going from the flute into the room, some of the sound actually bounces back into the flute. Or with the example you had in the lab, you had a tube of glass, and we were sending waves down that tube of glass by holding a tuning fork above it. and the waves were bouncing on the surface of the water, that's obvious, right? That there's going to be reflection there. But then the wave that was moving up doesn't necessarily just escape the tube. Some of it does bounce back. Some of it escapes because we heard the sound also. But at an interface where the medium is free to move, you do have some reflection of the waves. So we set up a standing wave there too. Now the interface between the water and the air molecules there are hitting the water, so they cannot oscillate with high amplitude. But at the opening of the tube, the air molecules there are free to oscillate. There's nothing to prevent them from oscillating, so you can have an antinode there where the air molecules oscillate with high amplitude. So what you need in a case like that, the tube with one open end and one closed end that you had in the lab, the closed end must be a node in terms of displacement of the medium, because the medium is actually hitting something hard there. And the opening of the tube has to be an antinode. And then you can only draw waves that have that characteristic of having a node at one end and an antinode at the other end. And that's how and once you draw the first few of those, you'll see that the condition there is that in your length of air that's oscillating, you can only have 1/4 wavelength or 3/4 wavelengths or 5/4 wavelengths. That's what you did in your pre-lab for that lab. So that's how you get standing waves. The idea is that you always have waves bouncing back and forth between two boundaries of a medium, and that's how you get those waves moving in opposite directions. But it can only happen between two boundaries, and the boundaries can be fixed or open, and then there's different conditions.
Okay. So you were also talking about nodes and antinodes?
Yes.
So how would you describe these in terms of interference?
If you want to do it in terms of interference, the nodes are where you basically have destructive interference between the two waves traveling in opposite directions. It's really points where crests are always meeting troughs and troughs are always meeting crests, so that the waves are always the opposite of each other at that point. And that's why the medium, when you add the contribution of both waves, the medium doesn't move at all at those points. So those points are, in a sense, points of destructive interference. And the antinodes are the opposite. It's where crests of one wave are always meeting crests of the other, or troughs are always meeting troughs. And the two waves are always in phase at that point. And that's why the medium gets large oscillations at that point. So the antinodes would essentially be points of constructive interference of the two waves moving in opposite directions.
I see. So we're gonna kind of circle back to two waves traveling in the same direction now?
Yes.
So how do we find then, like, whether there's destructive or constructive interference when, like, the waves are superimposed on each other?
Right. So again, it's a question of if crests are meeting crests and troughs are meeting troughs, or if crests are meeting troughs and troughs are meeting crests, right? So if the two waves are perfectly aligned, right, with crests on top of crests and troughs on top of troughs, both waves are doing the same thing to the medium at the same time. So if one wave is making the medium oscillate upward, while the second wave is also making the medium oscillate upward at the same time, then you'll get a large displacement of the medium. If one wave wants the medium to oscillate upward, while at the same time the other wave wants the medium to oscillate downward, then the medium will do nothing as a result. So it's really a question of, you look at the two waves, you can draw them one on top of the other, and if they're perfectly aligned, then you get constructive interference. But if they're perfectly misaligned, right, they're perfectly out of phase, with crests of one wave aligned with troughs of the other, then those two waves, they just completely cancel. Now, in general, you can have any case in between. The phase difference between the two waves doesn't need to be 0 or pi, right? You don't need to have both waves perfectly lined up or both waves perfectly misaligned. You could have anything in between. But in a lot of cases, we look at the extreme cases where you have perfectly constructive or perfectly destructive interference. Note also that we're always limiting ourselves to the case where both waves have the same amplitude. Because if one wave had a bigger amplitude than the other, then you wouldn't get perfectly destructive interference. But we simplify things in the course by limiting ourselves to waves with the same amplitude. And there's an equation on the formula sheet, right, for two waves moving in the same direction. It says 2a cos of delta phi over 2 times sine of kx plus or minus omega t, or something like that. The 2a cos of delta phi over 2, that is the resultant amplitude for two waves traveling in the same direction. The delta phi is the phase difference between the two waves. And if you can just check if the phase difference between the two waves is 0, then that means that the waves are perfectly aligned, right? So you have crests on top of crests and troughs on top of troughs. And if you plug that into the equation, 2a cos of delta phi over 2, where delta phi is 0, you get 2a cos of 0. Cos of 0 is 1, so that means your amplitude in that case is 2a. And that means perfectly constructive interference. If the waves are perfectly misaligned, it would mean that you have crests on top of troughs, right? And therefore, delta phi has to be, if you have crests on top of troughs, it's because you've taken your two waves that were perfectly aligned, and one of them has been shifted by half a wavelength or half a cycle. And that corresponds to pi radians, because one full cycle is 2 pi radians. So if one of the waves is pi radians out of phase with the other, they should interfere destructively, because you'll have crests on top of troughs. And if we look at our equation on the formula sheet, where the amplitude is 2a cos of delta phi over 2, if you plug a delta phi of pi in there, you'll get 2a cos of pi over 2. But cos of pi over 2 is 0. So the equation is telling you when the phase difference between my two waves is pi, you get perfectly destructive interference.
Okay, so this phase difference that you mentioned, we've
Yes.
seen two of them. One is the inherent phase difference,
Yes.
and one is just the phase difference.
Well, okay,
So
the phase difference can come from two different, there can be two explanations for it. So let's say you have, there's a bunch of problems in our practice sets and our assignments that we give students that involve two speakers, right? So you have two loudspeakers, they're producing sound, and when we say that they're in phase, it means that both speakers are creating crests at the same time and troughs at the same time. So they're in sync with each other, basically. Okay, and in that case, the only possible source, if you're at a place where the two waves are adding up destructively, it can only come from the fact that one of the waves has had to travel a bigger distance to reach you than the other wave, because they're both producing crests at the same time and troughs at the same time. So if both waves travel the same distance to reach you, then the crests of one wave and the crests of the other wave will reach you at the same time. So but if one of the waves has to travel a bigger distance to reach you, then it makes the crests and troughs no longer necessarily in sync with each other by the time they reach you. And then in order to get destructive interference in such a case, one wave would have to travel an extra half wavelength to reach you, or 3 half wavelengths, or 5 half wavelengths, because the shift that would introduce, if you take two waves that are aligned and you shift one of them by half a wavelength, then all of a sudden you've brought crests of one wave in sync with the troughs of the other one. Okay, so the total phase difference can come from the fact that you're at a point where one wave had to travel a bigger distance than the other one to reach you. That's one possible source of the total phase difference. But the other possible source of phase difference is the speakers don't need to be emitting crests at the same time and troughs at the same time, right? So the speakers could be out of sync with each other. It could be that one speaker is emitting crests while the other one is emitting troughs, and then they would be perfectly out of phase with each other. Okay, and then that would mean that if you're standing at a place where both waves travel the same distance to get to you, but one of the speakers is emitting a crest while the other one is emitting a trough, then at that location, what you're receiving is a crest from one speaker and a trough from the other speaker at the same time. And those will cancel, and you would have perfectly destructive interference. So you have to take both things into account, right? And if you move to a place where one of the waves travels a bigger distance to reach you than the other one, even though one speaker is emitting a crest while the other is emitting a trough, you can get the crests from both waves to be back in sync with each other if one of the waves travels an extra half wavelength to reach you, for example. So then the total phase difference could be made to be 2 pi. So it would start out as pi because one of the speakers is emitting a crest while the other one is emitting a trough. So your inherent phase difference would be pi. But then if you add to that a path difference of half a wavelength, which corresponds to pi radians, then you can make the total phase difference 2 pi, and then you get constructive interference again.
I see. Okay. Well, like along with this part of the unit, we also got introduced to beats. And that was kind of like confusing for me. Like, is this phase difference tied to beats somehow, or?
It's actually not. No, so you have to be careful. When we're talking about superposition, when we're doing waves traveling in the same direction, right? We're making a few assumptions there that maybe we don't make explicit enough every time. We're assuming we have waves that have the same amplitude, and we're assuming we have waves that have the same frequency and wavelength. Okay. That's what we assume when we're looking at perfectly constructive and perfectly destructive interference for waves moving in the same direction. And it's what we assume when we look at standing waves. Okay. But what we're looking at when we talk about beats is you're adding two waves that have slightly different frequencies. So we're no longer looking at identical waves. We're looking at waves that are slightly different in terms of their frequency. And what happens then is that since their frequencies are not quite matched to each other, if you imagine that, imagine two people just clapping their hands, right? And one of them claps their hands every second. And the other person claps their hand every 1.1 second, right? So their first clap will be synchronized. Their second clap will be 0.1 seconds apart. The third clap will be 0.2 seconds apart. The third clap will be 0.3 seconds apart. And the difference between the claps will keep growing, right? So that at some point, you have one person clapping and the other person clapping 0.5 seconds later. And it looks like they're completely clapping out of sync with each other. But then the difference will keep increasing. And if the difference between the claps becomes 1 second and one person is clapping every second, then all of a sudden they're clapping in sync with each other again. Right? So, but then they'll be 0.1 second apart and 0.2 and 0.3 and 0.4 and 0.5. And when they're 0.5 seconds apart, it seems like they're completely out of sync with each other. So what happens is the fact that they're clapping with slightly different frequencies means that there will be times when they're clapping almost at the same time. And then there will be times when they're clapping completely not at the same time, completely out of sync with each other. And that's what beats are. Okay, there are times when the two waves are in sync with each other and they add up to give you a wave with a high amplitude. And then there's times a short time later when they get completely out of sync with each other and they interfere destructively and you get low amplitude. And then they get back in sync with each other and you get high amplitude. And they get out of sync again and you get low amplitude. And that's what we hear as beats. When you have beats, you hear an amplitude going up and down, up and down, up and down. And that's but that's due to the fact that you're adding waves that have slightly different frequencies. We're not talking about identical waves anymore. The phenomenon is due to the fact that the waves have different frequencies.
See, okay. That makes it like a bit clearer.
Okay.
So I guess we'll have to whoosh back a little bit for this one.
Okay.
I think also in that unit we were introduced to like 2D and 3D waves from two sources.
Sure.
And we were supposed to draw the diagrams of how they interfered with each other and then identify antinodal and nodal lines.
Sure.
Like, how do you find where these lines are?
Right. So to represent waves in 2D, you have to use wavefronts. right? You draw these solid lines that represent the locations where you have crests of the wave. And if the waves are spreading out in 2 dimensions, then those wavefronts will be circles centered on the source of the wave, right? And the distance between the wavefronts is 1 wavelength. And if you have 2 sources, what you'll have is 2 sets of concentric circles that sort of overlap each other. And where these lines are crossing, it means that a crest is meeting a crest. And if a crest is meeting a crest, then that's a point of constructive interference. You also have places where a trough is meeting a trough. And that's also a point of constructive interference, because there the 2 waves are doing the same thing at the same time. So by joining together points where crests meet crests or troughs meet troughs, you get these lines that are actually mathematically they're hyperbole, and those lines are where the 2 waves are having perfectly constructive interference. On the other hand, if you have places where a crest is meeting a trough, or a trough is meeting a crest, those are places where the 2 waves are doing the opposite of each other. And that's where they cancel. And by joining these points together, you'll see that you also have hyperbole, but where you have destructive interference. So that's how you would do it. You look for points where the 2 waves are where crests meet crests or troughs meet troughs, and that tells you where you have constructive interference. And you look for points where crests are meeting troughs or troughs are meeting crests, and that's where you would have destructive interference. And then you see this pattern appear where these lines are all hyperbole.
So is there a way to identify how many of these lines we should draw? Or do we have to actually map it all out and count?
I mean, yeah, there's mathematically there's ways of figuring out, how many lines exist, but I think for the purposes of I don't know if you did a worksheet in class with it. A bunch of students might have. There's a worksheet that we have available to teachers where you can do that. There's few enough that you can actually just do them all by hand and figure out how many are present, right? But it really depends on the distance between the 2 sources and how many wavelengths are present between the 2 sources. That's how you would sort of figure out how many lines there are. But what you're trying to do is draw lines. The lines you draw represent places where the path difference is a constant, right? So right in between the 2 sources, you have a straight line that represents delta R equals 0, right? Because you're equidistant from the 2 sources, right? And that line is where, if the sources are in phase, that line is constructive interference, right? Crests will always meet crests and troughs always meet troughs right in between the 2 sources. And then on either side of that, you'll have a line where the wave from one speaker has traveled 1 wavelength more than the wave from the other speaker. And that's going to be constructive interference also, if the waves are in phase. And then if you keep going away from the center, you might have a place where one of the waves has traveled 2 wavelengths more than the other. And then you'll have a place where one of the waves has traveled maybe 3 wavelengths more than the other. But at some point, when you move away from the center, you're going to hit one of the sources. And then once you hit the source, then that's you can't fit more lines. The lines all pass between the sources. So that's it. Really depends on how far the sources are from each other to know how many lines you can fit there. But you have to remember that the lines are really places where delta R is 0 or one wavelength or 2 wavelengths or a whole number of wavelengths for constructive interference for sources that are in phase with each other.
Okay, I see. And
this would all be a lot easier with
actual
visual. It's hard to explain just with words, unfortunately.
So I guess the recommendation is to do the worksheet.
Absolutely, it's a great worksheet for visualizing what's actually happening in 2D when you have 2 sources. Yeah,
I see. So I think this is kind of our final conceptual question.
Okay.
It's what is the Doppler effect and why does it occur?
All right. Well, there's two different ways of getting the Doppler effect. One is if the source of the wave is moving, and the other is if the observer is moving. And physically, the explanation is different in the two situations. It leads to the same result, which is if you have an observer and a source, and if the source is approaching the observer or the observer is approaching the source, the frequency that will be perceived by the observer will be higher than the frequency emitted by the source. And you experience that in everyday life. If there's a car coming towards you, the pitch of the sound you hear from the car is higher than if you have a car moving away from you. And similarly, if the source is moving away from you, or if the observer is moving away from the source, the frequency perceived by the observer is lower than the frequency emitted by the source. Now, the reason for that is different if the source is moving or if the observer is moving. If the source is moving, if we go back to the idea of a diagram showing the waves spreading away from a source in 2D, where you have all these circles that represent wavefronts. If the source is standing still, all the circles will just be concentric with the source at the center, right? So the wavefronts that were emitted longer ago will now have moved further away from the source. Those would be the big circles. And then the ones that were emitted later are smaller and smaller and smaller circles, but they're all centered on where the source is sitting. If the source is moving, though, then the wavefronts that were emitted long ago are centered on where the source was when the source emitted those wavefronts. And as the source moves, the wavefronts that it emits, they all get shifted sideways because they're all centered on where the source was when those wavefronts were emitted, but the source is moving. So you'll have a bunch of circles that are no longer concentric. They're all shifted a bit to one side. And what that does is in front of the source, all the wavefronts get squished closer together than they would be if the source wasn't moving. And behind the source, all the wavefronts are farther apart from each other than they would be if the source wasn't moving. So what's happening there is that physically, in front of the source, the distance between crests of the wave is shorter than the wavelength of the wave if the source is standing still. And behind the source, the distance between crests of the waves is longer than the wavelength of the wave if the source is standing still. So if you're an observer and you're standing in front of the source, you've got all these crests moving towards you, and they're moving at the speed of the wave, normal speed of the wave, but they're closer together than they would be if the source wasn't moving. So if you have got these crests that are close together, they're all moving at the normal speed of the wave, then you will be receiving them at a rate that is faster than you'd be receiving them if they were more widely spaced, because they're closer together. So you're receiving them, the time between you receiving any two of them is shorter. So that's why the period is shorter and the frequency is higher. So physically, the wavelengths are shorter in front of the source. Behind the source, it's the reverse. The distance between wavefronts is longer. So the time between you receiving two successive crests is longer. So the period is longer and the frequency is lower. So that's what's happening when the source is moving. It's the actual wavelength behind and in front is shorter or longer than it would be if the source was standing still. And that's what leads to you perceiving a higher frequency if you're in front of if the source is moving towards you, and a lower frequency if the source is moving away from you. When the observer is moving, it's different. You can imagine a source just sitting there and it's emitting crests, it's emitting wavefronts, and those wavefronts are all spaced by the wavelength, lambda, in all directions around the source, because the source is just sitting still. So the wavelength hasn't changed. But if the observer is moving towards the source, then you have these wavefronts approaching the observer, and they're moving at the speed of sound, right, at the speed of the wave. But the observer is moving towards them. So the speed at which they're approaching each other is bigger than the normal speed of the wave. So even though the distance between the crests is really still one wavelength, the rate at which you're receiving them, if you're an observer and you're moving towards those crests, the time it takes for two successive crests to reach you will be shorter because the speed at which you're approaching you is bigger because you're moving towards them as they move towards you. So the relative speed between you and the crest is increased. That decreases the amount of time between any two successive crests, makes the period shorter, so the frequency higher. And if you're running away from the source, then the wave crests they have to catch up with you. So they're approaching you more slowly than if you were standing still. So even though, again, the distance between two crests is just the normal wavelength, the time between two crests reaching you will be longer than it would be if you were standing still because you're moving away from the crest. So they're effectively approaching you at a speed that is lower than the normal speed of the wave. And it takes longer for two crests to reach you. So that makes the period longer and the frequency lower. So the physical explanation is different in both cases, but the end result is the same.
I see. Okay. So that is it for the conceptual questions. And now we just have like general test concerns. So
yes,
there's been a lot of equations in waves. So what should we do during the exam if like we don't know what formula to use, or if we have like a weird variable pop out and we can't locate it on the formula sheet?
I mean, the formula sheet is pretty exhaustive in terms of the formulas you need to know for this midterm, right? They're pretty much all there. I mean, the ones that aren't there are ones that you're supposed to sort of be able to work out quickly on your own, like the conditions for wavelengths on a standing wave on a string, right? Those you just do a few drawings and they're there, right? You can figure them out on your own. Everything else is pretty much there. I mean, you have the equation for two waves traveling in the same direction. You have your equation for simple harmonic motion. You have your equation for a traveling wave. You have omega square root of k over m. You have v square root of t over mu. All these things, the Doppler effect is there. The trick there is you have to choose the right signs for your observer or for your source, depending on the situation, and you have to justify that clearly. But what I would say is the equations you're going to need to use should be pretty obvious from the question itself, right? I mean, we've done 3 chapters. One chapter was simple harmonic motion. It's a mass on a spring. So that one, the equations that are relevant, you have the kinetic energy and potential energy equations, right? The 1/2 mv squared and 1/2 kx squared. You have F equals minus kx. That's the force from a spring, Hooke's law. You have the omega is square root of k over m, telling you what the angular frequency is going to be given a certain mass and a certain spring. And then you have the equation describing simple harmonic motion. X of t is a cos of omega t plus phi naught. They're all there. And if the problem you're looking at is a problem of simple harmonic motion, those are the equations that you're going to have to use. The second chapter we did was traveling waves. All right, in that one, you have your displacement of x and t equation. D of x and t is a sine of kx plus or minus omega t plus phi naught. That's the main equation that you're using. And then you have to remember, I mean, k is 2 pi over lambda. That's your wave number, radians per meter. Even that one, it's on the formula sheet. But if you don't remember, the wave number is simply radians per meter. And you know that in one full wavelength is one full cycle. So there's 2 pi radians in one wavelength, 2 pi over lambda. The same thing for omega is 2 pi f, or omega is 2 pi over the period. There's one full cycle in one period of time. One full cycle is 2 pi. So 2 pi radians over the period is omega. So those even if the formulas weren't there on the formula sheet, you can easily sort of remember them just by thinking about the units there. So I would say, identify what the problem is asking about. So you have simple harmonic motion. You have the second chapter was on waves. And then in that one, we also did the Doppler effect, which is on the formula sheet. And we also did decibels, which are on the formula sheet, right? So if it's a problem about sound intensity, you're going to have to do decibels or something like that, right? If it's a problem where you have a source is moving and an observer is moving, you know that's the Doppler effect, and then you'll have to use that equation. And then we did superposition, and then there's 3 different cases, right? You have waves traveling in the same direction, and you have waves traveling in opposite directions, where you get standing waves, and we also have beats, where you have waves with different frequencies. And those are sort of the 3 different cases that we've looked at. So it should be pretty obvious from the content of the question which of these main topics we're aiming for. So hopefully, if you do enough practice problems, you'll be able to identify the questions, right? But it's really, there's simple harmonic motion, there's waves, traveling waves, there's the Doppler effect, there's decibels or intensity, sound intensity, there's waves in the same direction, there's standing waves, and there's beats. Those are the main topics that we've studied. It looks like a lot when you're in the middle of it, but when you step back and you look at what we actually learned, there's a limited number of topics there. So hopefully you don't get too confused about what equations you should use, because the physical concepts that apply to each question should be obvious to you if you've practiced enough.
Okay, so do you have any final tips for us when we're writing our solutions?
Yes. Okay. So a good thing to do is to have a look at the whole exam before starting to answer, because that helps you plan your time. Okay, you have a limited amount of time. Hopefully, you have time to do everything. Right? We're not giving you we make our tests so that students have time to answer all the questions if you know what you're doing. But in the case where maybe you run out of time, you want to make sure that you don't run out of time to do questions that you know you could have done. So have a look at the entire test and make sure that you start by answering all the questions for which you're sure you know the answer. And all those points will be in the bank, and you build up your confidence, right? So get those out of the way right away. And then start working on the ones that you think you know what you need to do, but you know you're going to need a bit of time, and you're going to have to think a little bit before you know exactly what to do. You're going to have to maybe try a few things, or so manage your exam. Start with the questions you're sure you're going to get, and then move to the ones where you're pretty sure you know what you need to do. It's just that it's going to take you a bit more time and thinking. And then if there's a few questions that you think are a bit harder for you, then keep them to the end and only come to those once you've made sure to sort out all the ones that you know you can get. That way, if you do run out of time, you're running out of time for questions where maybe you wouldn't have been doing super well anyway, so it doesn't cost you as much. So that's one piece of advice. The other piece of advice is when you're writing, so obviously for multiple choice, you don't need to justify anything, right? You just circle the right answer, hopefully, and then you're done. But for any other questions, you need to justify your answer. So don't assume that the teacher knows that you know what you're doing, because we don't, right? We don't know if you're guessing. We don't know if you just got lucky. So make sure you justify, show us your reasoning. And that does 2 things. So first of all, it's required. And second of all, it makes it a lot easier for us to follow your reasoning. And if something ever goes wrong in your solution, if it's very clear where you went wrong, I mean, we'll penalize you for the thing you did wrong. But if you're being internally consistent with everything else, it's really easy for us to go, oh, okay, I get what was going on here. The only thing that happened is, oh, you missed a factor of 2 in your algebra here, but everything else is perfect. You'll get 9 out of 10. But if you're not justifying anything and you make a mistake halfway through the question and we can't tell where the mistake came from or what the mistake was, you're going to lose a lot more marks, right? We can't give part marks for things that we don't see on the page. So it's good for you because, I mean, it helps us understand your reasoning and give you all the marks that you deserve for everything that you've shown to us that you understand. It makes it easier for you also to double check your work and catch your own mistakes if you've made mistakes here and there. And hopefully you have time to review a bit at the end. So yes, try to present your work clearly and justify all your steps so that your teacher knows that you know what you're doing. And then we can give you marks for what you actually know how to do.
Okay. Thank you for
all right.
all your time, Professor Vinet.
You're welcome.
It was really helpful.
Okay, I hope it was, and good luck, everyone. And go and see your teachers during office hours and practice with each other. Don't do everything on your own, right? The worst thing you can do is try to just do all the problems on your own and understand everything on your own. Go ask questions to your teachers. Go ask questions to any of the teachers. We're all happy to help you if your teacher's office hours don't work with your schedule. You can come and see anyone whenever you want. And work together, study together. That's really, really helpful.
Yeah. Okay.
All right. Okay.
Thank you, Professor.
Thank you.